All right, let's get started. I'm back from vacation today. I'm catching up on PRs. I got through about a third of them today, so another day or two. Yingjin, how's it going?
Yeah, last week I noticed an issue of an unexpected trim spike here. So, and the generational GC code and the performance analysis is mostly down here. Uh, and the analysis shows that due to generational GC, a desired bimodal distribution has been formed. And we also can see the benefits from the improved GC policy from the reduced write amplification, reduced conflicts, and improved end performance. And I think generational GC can also be a base step to implement device tiering. And I will finalize the PR this week for review. And I also got a clue about how to evaluate the SSD internal write amplification, and I will have a try to do some evaluation later. That's all.
That is great news. Cool.
Mhm.
Aravind, how's it going?
Hi. Yeah, so I sent a peer. It's still in draft state. I sent the peer number in the chat. So there are like around five commits in that. Most of it is cleaning and a couple of correction of calculations in the make metadata function. Apart from that, I'm working on. So what I was seeing was one issue when I start OSD, it would try to read all these segments and then try to write the header and then write the tail, and the tail was getting written at the end of the segment. But that will not kind of work with ZNS because it has to write at write pointer. So I made the changes to write the. So my plan is to ensure that when we close the segment, we write this tail information, right? So when we close the segment, you write the tail at write pointer, and when you try to read the segment, then you read it from the write pointer minus or whatever that offset 4K offset, and to get the tail information from there. So that is what I'm trying to do. I'm done with the write path, and the read path. I'm seeing that there is no at least as of now, I couldn't find an easier way to get the right pointer in the read path. When we do a read segment tail, that function basically in the segment manager, that in that path there is no easy access to that segment right pointer. So I'm kind of currently looking at making adding new functions to get that information at right pointer. Um, so yeah, so that's where I am at, and uh, I just had one question for the team, like in the block segment manager, right? So do we cache the segment information, all the segments information, or is it something that we calculate every time or read every time, like the right
Yeah, on
pointer?
startup, I think well, not the write pointers since we only have a few of them open for write at a time. And we should be able to keep the write pointers in memory. Do you mean the write pointers or do you mean the end of the segment?
The right pointer.
Okay, so just for the couple of, there's in-memory state that tracks the current write pointer for every segment.
Yeah, yeah. So I
Every
saw one
every segment that's open for write, that is.
only for those which are open for write.
The ones that are closed do not have write pointers. They have an end, but they do not have a write pointer. You can't
So
reopen a closed
okay,
segment,
okay,
right?
you can't reopen a closed segment.
On a ZNS device in general, like once you've closed a segment, most devices don't let you reopen them.
Um, no, I was asking about in general, like we have this block implementation, right, in Ceph, in Crimson. So
Yeah.
in that one, do we reopen?
No, because the point of the segment manager is to mimic the behavior of a ZNS device. The block segment manager isn't supposed to be any more powerful than a ZNS segment manager.
Okay. Okay. So in ZNS, we can reopen a closed zone. So there is the option to transition from closed to open state, but it is not much of a benefit in the sense that both a closed zone and a open zone are considered as active resources in the spec. So so there is no real benefit in actually closing the zone versus a finishing the zone. Finishing the zone actually, when you say you finish the zone, then that zone is not available to write unless you reset it.
Sorry,
Whereas,
that's what I meant. We don't bother with close because it's pointless. I meant finish. You're right. Closed zones don't seem to have any purpose. So, sorry, what I meant was we only track the write pointers for zones that are not yet finished. That is, the relatively few zones that are open for write.
okay, but when you, okay. So for zones which are open, you track the write pointer. And one more question I had was the for the Crimson OST, what is the default? I mean, in SeaStore, what is the default write manager like? I mean, do we use the ZNS segment in normal cases, or ZNS? I mean, the segment manager. I'm sorry, segment manager is specific only for ZNS use case.
We're not sure yet. For ZNS devices, obviously we'll be using a segment. For non-ZNS devices, it will depend. There are Flash-based devices that actually prefer append-only write workloads. So in that case, it will likely make sense to use the block segment manager. For faster devices, it will make sense to use the random block manager that we're still working on. Does that make sense? So it will both options will exist.
Right. So if we want to currently, if I want to run SeaStore on a regular SSD, not a ZNS SSD, which does the segment manager, because segment manager has these three implementations I saw. One is the ZNS, one is the block, and one is the
Ephemeral.
ephemeral, yeah. Ephemeral. So those three implementations are there, and my understanding was that for ZN, if it is a ZNS drive, the ZNS implementation comes into picture, and if it's a regular SSD, then the block implementation comes into picture. Is that wrong?
No, that's exactly right, and it's supposed to auto detect and use the right one.
Right. Okay. Yeah. I'm saying that all of those calls are getting wired to the ZNS segment manager calls. So that was my understanding. So okay. So if I use a regular device, then it should all go to block segment calls, right?
That's the idea.
Right. Okay. Okay.
And to complete that, the ephemeral one is just an in-memory implementation for unit tests.
Right. Yeah, I got that. Okay. Thanks.
Cool. Chenmei, how's it going?
I'm working on the PR according to the comments and fix list object issue. No, root cause the issue and working on the PR now. So that's all.
Okay, cool. Oh, Aravind, Yingzhen linked two places in the segment cleaner where we actually do maintain written to. But I think what you're asking about is within the segment manager, which is a little bit different.
Yeah, so the return to tracks whatever is amount of segment used, right?
Yeah, that's the idea.
Yeah.
And we do cache that on startup.
Right. Yeah.
Radek, how's it going?
Hello. Two things. First of all, is PR for handling set allocs hints at the layer of execution. Another thing is the long story of GCC 11 for Crimson building in CI/CD? Well, Crimson builds. I'm still working on the problem with Python bindings compilation. Internally, it uses Python's dist utils and GCC instantiated from there. Unfortunately, goes to wrong assembler program, to older version, the one that is not the default system one, which doesn't support one of the options. Right now, putting more debugs in the code of Python's dist utils just to understand what's the reason. That's me.
All right, Zweihan?
Last week I was trying to fix several bugs I observed when I restart a Crimson OSD. One of which is this. I'm pasting it in the chat window. And I also did some further performance analysis for the GC process. The result shows that first I run the test for 2 hours, and it seems that the whole test procedure can be split into 3 phases. The first is that when the disk space is not used up and there's no space reclamation processes running. And the second is that the space reclamation processes join in and the disk space is used up. And the third phase is about after about 50 minutes since the start of the test, after which the time of the space reclamation process overruns all other GC cycles in terms of durations. I think the journal for the journal trimming cycle duration, it also drops following if it drops in those 3 phases. And I think the reason is that as the test runs, the cycles per unit time of the GC journal trimming process drops, and this is because I observed a very similar curve pattern between the journal trimming cycles and the journal trimming durations. For the third phase, I think the reason why the space reclamation duration increases is that after about 50 minutes of running the test, there came up a lot of backgraph merge operations during the space reclamation cycle, and that time the time it takes made the space reclamation duration longer. There are several other observations. The first is that although the journal trimming durations, the journal trimming time drops as the time goes on, and the number of extents that committed by journal trimming transactions are actually increased. So I think maybe if we can increase the number of extents rewritten by a single journal trim transaction, and without increasing any overhead of the conflicts, we can have some kind of performance improvement. The second extra observation is that as to the journal trimming process, most of its time is spent on committing the transaction. So I think if we can the transaction commit time also occupies a significant part of the whole space reclamation duration. So I think if we can implement some kind of pipeline between the GC cycles, I think maybe we can make the GC more possible to be scheduled to run, and so the I/O throughput curve can be smoother. Right now, the curve is very rough. There is another observation that if the I/O is blocked, then the journal trimming transactions commit time is significantly lower than when the I/O is not blocked. So I haven't been able to dig into it, but I think there may be some extra optimization point in that part. I also did some CPU profiling for the GC process. It seems that after our previous work, there is almost no solely I/O waiting time for the Crimson OSD, and the CPU is kept busy. So I think the next step, if we want to increase the I/O throughput, we need to reduce the work for the GC processes. It seems that right now the most significant part of the CPU time used by GC processes is that at various phases, the SeaStore needs to get LBA nodes or backref nodes from cache, even if they are already in memory. I set the size of the cache URL to about 1 gigabytes. So most of the LBA nodes and backref nodes are in memory. So I think this means that getting LBA or backref nodes from cache might be an overhead, and if we can save it, we can significantly reduce the workload of the GC processes. That's basically all the perf analysis results. That's all.
So just a couple of comments. We absolutely do have to add the object data blocks to the cache when we're doing GC. It's for correctness reasons. While the I/O is in progress, any future I/Os that come in on that block need to be able to see the projected future state. So that part's mandatory. You're correct that it does pollute the GC or the cache, which means we shouldn't be adding it to the LRU. But I believe that optimization is already implemented. The larger observation here is that indeed we are CPU bound now, so that's good news. The data structures underpinning the cache and the LBA tree are very, very simple. The cache in particular is just using an intrusive map. There's nothing clever going on there. So that's where I would probably start. I would probably start by investigating how much we can improve the cache data structure itself, as well as the way we're doing lookups in the LBA tree. Like, I think we're doing linear scans. We're not even doing binary searches on the blocks, unless that got improved already. So there's like a lot of space for improvement there. If I were you, I would start by making a micro benchmark for looking up a block already in cache. Like pre-populate the cache with a bunch of, or pre-populate SeaStore with a bunch of LBA nodes that are already present, and then measure the time it takes to do 1,000 random lookups or something, and then profile that.
Okay. Okay. I'll follow that direction.
That's, I think, where I would start, and then I would start optimizing from there, depending on what shows up in the profile.
Okay. Okay.
This is good news. Okay, cool. Anyone else have anything they want to talk about? All right, have a good week. Later.